Okay. Hi, everybody. I think I'm ready to do this. Hopefully you're ready to watch it. Welcome back. We are, what are we, lordy, we're in week 10. It's a quiz this Friday that I will, let's assume it have emailed you about. Um, um, I don't know. Otherwise, I'm just going to continue talking about Spark. This week's exercise is the first about Spark. Maybe make a note, like, Spark is it's a big tool. There can be like compatibility, there can be weird setup things. Usually not. It's definitely gotten better, but keep an eye on it. Don't start the last minute is what I'm saying. Okay. We were here. I was writing this code, and this is I'm reading a CSV. I'm reading a collection of CSV files with Spark. So this, like in Pandas, that would have always been one file. Spark prefers a directory of many files, which is what I've done here. I think on the slides I'm implying it's one, but I'm going to do the more honest thing for the demo here. I've got three. I mean, they're all very small files for the demo because demo, what are you going to do? But this reads all of them, which is a good thing. So there's no header rows here, and Spark does have to know both the names of the columns and the types of the columns. That's what I'm doing here. Specified the schema. And then, it's kind of where we left off last week. You do like the kinds of things you can do with pandas. You spell it differently, but it's the same kind of thing, right? Like keep only the things that have this property. Like, so this is some kind of an expression, obviously, right? Like it's, look at this column, compare each entry in that column to 5,000. If it's true, keep it. So have a data frame with like the same columns, fewer rows. And then this is like a SQL select. It's from this data set, keep only these columns. Or I guess it's create a new data set out of the old data set with only those columns. And maybe I don't like the way I've spelled that, actually. I'm going to call these different things because they are different things. So take the thing called C1 and do some stuff to it to produce C2, and then have a look at it. And so instead of running, and I don't think I emphasized this last week, instead of just running as a Python program, Spark code probably you're going to have to run as a Spark job. Because, okay, running locally here on this computer, fine, whatever, it's just running. But in general, Spark Submit is a lot smarter. When you run the exact same command with the same code on the compute cluster, it knows, oh, we're on a compute cluster. Send some work over there, send some work over there. So you kind of have to be inside that world. Don't be scared of the horrendous debugging output. What's happening here? Get subject is not supported. What does this mean? Ooh, is this a Python version thing? Wait, I did this last week. How did this not happen last week? I'm gonna have to pause. I remembered. I didn't mention this last week. There's just some like Spark, again, these are these things that happen. It's a big, powerful tool. It was sensitive to the Java version because it turns out it runs Java behind the scenes. If I tell it, hey, Java home is Java 21, not Java 27 or whatever I have as a default on my system, then it runs just fine. Yeah, these things are going to happen. I'll try to update some docs on that. But anyway, after all that, what I got, and maybe we should have a look before and after. Started with this, got rid of the things with small area, got rid of the area column in the next step, and I got there. Okay, fine. Right, I didn't get this far. I don't want to display big data sets on the screen mostly. That's not going to fit. Mostly what I want to do is, I'll write them to a file. But not a file, for the same reason I probably don't want to read a file. I want to be able to read a bunch of files all concurrently, and typing and talking at the same time is still hard. But what's about to happen here is it didn't create a file named Spark Output, it created a directory named Spark Output. With long and annoying file names, but hey. So what happened there is Spark is doing the calculation somehow concurrently, and each concurrent thing that's happening is producing a separate output file. I'm producing JSON. It's in fact new line delimited JSON, or JSON-L, which is what we've been seeing all semester because it's what I tend to use because Spark uses it. But I got that. I got this representation of my thing. Oh, and I guess it probably only wrote 2 files because I think what would have happened, as a little preview of something I'm going to say later, each one of these files got picked up by a separate worker, thread, or process, or something. One of them was emptied. Like, I only have 2 rows here, so pigeonhole principle. One of these must be empty after the thing. Okay, so if it had no data, it didn't bother to write an output file, so I only got 2 files in the result. But I actually did get concurrency there. It's not obvious, but I promise. And in order to think about what my output looks like, I have to either mentally or actually concatenate those files. Like, maybe I just have to think, my data is this directory of files. And I find some people are bothered by this, right? That, oh, how do I get it to be one? Don't get it to be one file. This is good. We'll talk about why. Yeah. So if you want to, like, this is probably debugging output. It shows you some sample of the thing. Okay, that's fine. Like, sometimes you want that. Sometimes you want to just have a little inspection of, well, hey, what's going on at this step? Is it what I expected or not? And at that step, it was that. I guess that's probably what I expect. And then by the end, I can have a look at the output. And again, is that what I expect? Hopefully. So I think you can tell, like, this is a very different tool than pandas. I guess it is and it isn't. Again, the kind of thoughts I'm having about the data are the same. I want to do this to every row. I want to keep this calculate a new column or whatever. I do find myself writing this pattern a lot, which is why I have, like, if you look on the course webpage, technical instructions, Spark skeleton, this sort of outline for things, it's what I just tend to write myself, partially because it's just good Python style, partially because I like having this, because then if I want to just, you know, if I've got 5 steps of calculation and something's going weird with step 3, I think I can do a, you know, step 3.show and just bail out right there, just so the rest of the stuff doesn't happen. I just look at that and then exit, and then of course comment those out and leave them in my code, so my code looks really ugly. Probably I should delete them, but you know what I mean. I also don't think it's bad to, again, like, as a debugging step, to do something like this. Just output that, and you know, is it what you expected or not? Especially with a bigger data set, right? You don't want to just dump it on screen. .show doesn't, it only shows you the first things. But you can do that. You can write to files some intermediate step. Just have a look, see what it looks like. You can ask, you know, are the columns what I expect? And I guess maybe for context, like, the reason I'm saying this, Spark can be hard to debug and to diagnose because, okay, a bunch of comparisons to 5,000 are happening, but if I'm on a compute cluster, those are not happening on the computer that I'm looking at, right? Like, I'm logged into some computer with SSH, but that computer is not the one comparing numbers to 5,000. That's happening somewhere out on one of the other computers in the compute cluster. So if something goes wrong, you're not going to get a super good error message. It's just, there's too much complexity between you and the code. So some of these things for like just how to get a handle on what's going on, you know, you end up back in the like just print stuff for debugging because it works. If you can get the data where you need to print it. So I'm going to assume many to most of you have written database queries in SQL. And yeah, like these look the same, or they feel the same. And in fact, they even look more the same if I replace filter with where. They're the same function. It's just one's an alias to another. Okay, if I use the word select and where, that really sounds like a SQL query spelled with a different syntax. You know, that's kind of not by accident. This is, these are words people use to talk about this kind of thing. The same kind of thing you can do in a SQL select. Again, if you don't know SQL, I forgive you. But like in SQL, you can do something like that, right? Well, I guess cities. And in fact, in SQL, you can then say as area in meters squared or whatever. So this is the same kind of thought. I'm creating two columns with this select query. I'm creating two columns with this Spark select method call. It's, again, the exact same thought with different syntax. I just want to take that number, multiply by 1,000,000. Or that whatever this is, whatever this object is in Python that represents this calculation, I can say, oh yeah, that, but give it a better name. Don't call it area times 1,000,000. That's a dumb name. I don't like that name. I like this name. Sure, fine. Again, the filter method does filter or where. You can spell it either way. It does the same kind of thing as the like condition in square brackets in, I guess, the pandas equivalent. Well, to that would be like, so in pandas, you do an in-place change, right? Like this is keeping the existing column and adding a new column. With this and with the Spark code, all of which do kind of conceptually the same thing, I'm creating a brand new data frame that has like the area column is in my city's pandas data frame. If I do it this way, it's not in these other ones. Yeah, it is what it is. And then the filter method that, you know, I could chain on here, even if it's kind of gross, is only keep things where this condition evaluates to true, exactly the same as I would do is the mod operator, is that a thing in SQL? Probably. In pandas, I would have to do this kind of thing. Yeah. And I guess if I wanted to actually kind of close the loop here, if I'm only going to keep the column city and area 1 in pandas, area M2, sorry, in pandas, I have to spell it this way. Okay, so now these blocks of code are all doing the same thing with Spark syntax, SQL syntax, or pandas syntax. Oh, I always forget that. I don't know that this is the best one of them, but it's not worse, right? Like, okay, I have to spell things this way in Spark. Great. The thing that I just did of like chaining like method after method, you can do it. I'm not sure it's the most readable code. I think sometimes people have like a feeling that this code is more efficient because I'm not like storing the intermediate result. That's not true in Python or in Spark. We will talk about why. But both of these pieces of code have the same memory footprint, I promise. Okay, so there's a lot of stuff you can do with a data frame, a Spark data frame, well, pandas data frame too. Again, like things like select and filter, these are probably the most, the big name ones. Should be consistent. But okay, there's a bunch of other stuff too. You can, I don't know, for some reason, maybe I want the first row. I guess this could be, I just did a group by kind of thing and I know there's only one row left. So, give me please. What did I talk about over here? Yeah, okay. This is one way to get rid of a column. This is one way to add a column. I don't know if you like, if you like saying this, like create the new data frame called C out of cities, but add this column, or this, like these are doing the exact same thing. Well, one of them is dropping a column implicitly. Same performance. Don't think that one of them is faster. They're doing the same operation with a different way to express it. In the same way that I can say cities.select and then list only the columns I want to keep, or I can say cities.drop the columns I want to drop. Exactly the same. Sort, okay. Yeah, might want to sort things. Maybe I want to just keep 1% of my data and do some simulation, whatever, those kinds of things. Or there's a few, like all of these create a new data frame. There's a few that don't, like do the calculation, return a number. Mostly though, it's going to be this data, new data frame equals old data frame modified somehow. And there's a lot of weird restrictions for Spark that they feel weird until you remember the context we're in, which is this is a big data tool. The assumption that kind of has to be made with all of the Spark methods and all the Spark, calculations and options and whatever, is that this is not in memory. Pandas makes the assumption that everything is in memory. In fact, it's not even an assumption, it's true. This data frame is a data structure in memory on my computer. So is this, and so is this. Those are 3 different data frames, but they are in memory. Spark data frames, well, maybe they're not in memory at all. They're certainly not necessarily in memory on one computer. They're partitioned. And a partition in Spark is like a subset of the rows. So it could be like the first, maybe I have 2 partitions and the first half of the rows are on this computer and the second half are on that computer. And well, if I had to do this, well, yeah, you can do this in parallel, right? Like if I have a billion cities in my data set, I could take the first half billion, multiply those areas by a million, and the second half billion on another computer, and at the same time with all, perfect concurrency, multiply those numbers by a million. And I can do the mod 2 equals 1 calculation the same way. That's what's going on here. So each one of those things I just described would be a partition. And they can be handled separately. What that means is you get concurrency, you get to use all your CPU cores on your, huge compute cluster with thousands and thousands of cores, or just on your computer with 4 CPU cores, you still get to use all of those CPU cores, and that is nice. I don't know if you know the term embarrassingly parallel, but it's something, well, it's something where the way to do it in parallel, like with concurrency, is obvious. Like this, if I have many, many, many rows in my Spark data frame, how can I use concurrency to do all of these multiply by a million operations? Well, in the really obvious way. If you have 100 CPU cores or something, or like just take the first 1%, do it. Next 1%, do it over there. Next 1%, do it over there. Like, I know it's not the origin of the term, but in my mind, embarrassingly parallel is short for it's embarrassing if you don't do it in parallel. Pandas doesn't. Pandas is what it is, right? Like, if I'm doing work in Pandas, there's basically a for loop being hidden from me. All the data's in memory, all the data is being operated on one after the other. Spark does the smarter thing, which is what I want. The partitioning of a data frame is usually invisible, and also really, really important. I have seen people that should know better make this mistake, where they have some massive data set and it ends up being in 2 partitions, and we'll talk about why that might be. Okay, then you can buy all the CPU cores you want. You are not going to use them. I have 2 CPU cores on this computer. I don't need a huge compute cluster to do this. But if I have a huge compute cluster and I want to use it, 2 partitions is the wrong number. So basically what's happening here is I kind of have to know, if I care about performance, that my data in Spark is partitioned. That's always true. Maybe I have to know how it's partitioned, how many partitions, because that controls the concurrency. One worker, whatever the worker is in Spark, is handed a partition and said, hey, do this work. When it's done, it can be handed another partition and another one and another one. You know, they get queued up, but I want to do the work faster if I have multiple cores, and this will get me there if I'm not dumb about it. So what I was seeing, like when I read 3 files off the disk and I said, oh, it turns out I'm now doing this work, work on each one of those files independently, it's because when I read a directory of many files, each file turns into a partition. So, okay, that's great, right? Because what that means is I can, if I have 1,000 input files, I can have, well, whatever number of workers I have, maybe it's 100. Okay, well, one worker can be handed one file and be told, okay, read that into a data structure and we're going to do stuff next. And another worker can be handed the next one and the next one and the next one. Okay, and each worker has to do like 10 on average or whatever, but that's fine. That can all be done perfectly concurrently. Nobody has to coordinate anything. It's embarrassingly parallel. And the same thing for a lot of the calculations we're talking about and when writing files. So like back here when I created, well, okay, I started with this and I produced that. So there's one empty file here that's just a marker that the thing succeeded. So you'll ignore that. What happened was 3 threads or processes or whatever thing you imagine in a computer doing work, it doesn't really matter. I think, like since I have more than 3 CPU cores, I think probably what happened is 3 workers got started up. Each one read one of these files. Each one did some less than 5,000 comparisons. Each one did this to keep only these columns and throw away those ones. And each one wrote a file in my output directory. One of them didn't have any file or any rows left after the filter, so it didn't write a file. It just said, okay, I got nothing, I'm done. The other 2 wrote their output. At no point in that story did any of those 3 workers have to coordinate with each other. Somebody had to get the work going. Somebody had to say, okay, you take this file, you take this file, you take this file. But after that, they just did their thing. And that's why. That's why I want my output to be multiple files in a directory, because then as long as everybody's looking at the same directory, everything happens concurrently, and I'm very happy about that. I want that. I have a lot of data and I have a lot of CPU cores. I really need this to happen. Or I guess in diagram, this. I should update this diagram. So this no longer happens. Like this empty partition used to become an empty file a version or 2 ago in Spark. Now this file just doesn't get written. And I got those 2 output files instead. But again, there's no like, I don't know, there's no crossing of these arrows, right? One process, one CPU core, one whatever is doing all of this work. Another one's doing all this work. Another one's doing all this work. Great. So this is why we have a directory of files as our input. We have a directory of files as our output. We are happy about that. You just have to remember to mentally combine all of those things. Don't be scared. I guess I've been doing this, haven't I? Like I was doing, so Spark output /star, that contains all of it. Usually what you have isn't going to fit on a screen if you have a big data set. So if you pipe it through some pager or something, you press space to go through it, press Q to quit. Or if the output is compressed, which we'll see, well, put it through something that knows how to deal with the compression and have a look. So all of that was just on my computer, right? That's a totally like legal thing to do. That's totally reasonable, because I do have more than one CPU core. I'm not going to get that with pandas, almost certainly. Like I'm not going to get any kind of concurrency. One of my CPU cores is going to be doing work. The other N-1 expensive CPU cores are going to be sitting there doing nothing. Okay, like I like running Spark to get data, to get work done on a kind of modest data set. That's not a bad idea, but not what we're doing here. I wanted, like I started this whole thing by saying, like more than fits on one computer. So, well, I need more than one computer. I need a compute cluster. So this is where the greater Hadoop ecosystem, I guess, kind of comes into play. So the things that are running on a compute cluster, ours specifically for this, Yarn, which again stands for yet another resource negotiator. Resource is a compute core or whatever, or memory. So when I say Spark submit on the cluster, I'm effectively giving an instruction and giving a request to Yarn. Hey, I've got some compute work to do. Maybe some hint about how big it is, maybe not. Maybe a whole bunch of your classmates are running jobs just then and you have to get queued up, but you know, that kind of thing. I want to run my logic, please. And the other thing that I said back here a little bit, if we're going to do this whole thing and we're going to have different workers reading different files and writing different files, well, they need to, you know, all kind of see the same files. And that's the problem for a distributed file system. That could be done with, you know, some kind of object store like Amazon S3 could hold your input files and receive your output files, but we're going to do it the Hadoop way, which is this distributed file system. Each computer in the compute cluster is going to both have some CPU cores to do work and have some hard drives to store data. These tools are responsible for managing all that because I don't want to. The way we've been doing it so far is the files are just stored on my computer, right? Like I can do the standard Linux thing and I can say ls that directory and I can see the files in there. And well, for compute work, again, they're just running on my computer, right? They're just here. But once I go over to the compute cluster, the data is being stored somewhere different. The compute is happening somewhere different. And you kind of have to remember this. If you're not thinking about it, the thing that happens is very confusing, I guess. Because, again, on my computer, fine, the input and output directories that I'm kind of imagining are specified on the command line here, and we usually will have them specified on the command line. That's just files. Files, you know, I can open up a file manager and have a look at. On the compute cluster, they're not there. The files you're storing are out here. The commands you're running are here. So what we're going to do, have I done this already? Yeah. So over this tab, so I've done this, right? That's the cluster gateway is the thing that's called cluster.cs.sfp.ca. I'm running commands here. The actual storage and compute work are happening on some other computer nearby. So if I do ls, oh God, it's time to clean up my home directory. But anyway, that's my home directory here. If I got to manage data, it's out there. So I can't do the standard Linux things on HDFS. I've got to do HDFS things on it like this. So I can list my home directory which is going to be a different collection of files in here. These are things that live out in the compute cluster. Also time to clean that up. And then like the input files that you're going to use for the exercises are there in kind of a common location, so you don't all have to upload them separately. What do you do? So like the very first thing you do this week is on this XYZ data, because it's just some fake data to have the first thing happen. You can download it. Like you can download and have a directory XYZ1 on your computer and you can use it. Or you can copy the exact same code over to the compute cluster. On the compute cluster, if you specify a directory as input, it will be an HDFS directory, not a local file system thing. So that means that like I can't do that, but I can do that. So it's not on the gateway. It is out there in the HDFS file system, and that's how I have to talk to it with these HDFS commands. And I guess you'll notice, right? It's partitioned. I've got 4 partitions that are all pretty modest, 100 kilobytes each. And then this is the sort of pattern for all of these data sets. There's sort of small, medium, and large. Like the small is the one that will be in the zip file that you're given as part of the exercise, as has been happening all semester. But then I can't give you a big data set that way. It's too big. On the compute cluster, there are bigger versions of that data set, a bigger subset, or a bigger subreddit or whatever, more time of data, whatever it is. And okay, this is still, it's 40 files. Each one of them is 29 megabytes. Okay, that's, bigger. It's still not huge in the modern sense, but fine. You can get data in and out of HDFS. It's an extra step, right? So this is, if I have a data set of my own, I have to first get it to the cluster gateway, like use SCP or whatever, then from the cluster gateway into HDFS, or in the other direction, my output to the cluster gateway, and then again, maybe copy back to my computer or whatever. If you want to see what's going on there, okay, so this is, these are gzipped files. So I'm going to hand them to something that knows how to deal with zip files and knows how to uncompress them once it gets them. Okay, this is what's in there. I have columns ID, XYZ that have whatever numbers in them. This, of course, goes on for a long time. What if I hit end? If I hit end, have I asked for something unreasonable? It has to go through all those files, ungzip them. We'll let it sit there. So I've got these, for lack of a better word, worker nodes. There's 4 of them in our compute cluster. Each one of them is handling chunks of files in a replicated way, which means that, if you want to read a file, there's 2 spots, like 2 computers where it can be read as a local file. It also means that if one of the worker nodes disappears, hard drive fails or whatever, there's some redundancy there and you're not losing data. And again, you can read them. Like if I run a Spark job on that data, okay, let's bail. Okay. Oh, again, when you're in less, always somebody who doesn't know this, press Q to exit. And yeah, this is, that error is just like, hey, there's a bunch more files you wanted me to read and I can't read them because, yeah, I don't want to show them all on my screen. That's fine. But what I do want to do is run the code. Where's my, please hold. Let me find the hint code for the next exercise. Ugh, I just had to download the zip file. Okay, so this is the zip file. Like there's nothing, there's no secrets here. I mean, you'd have to write some code. Oh, that's not the hint I want. This is the hint I want. That reads that directory of files. You're given one. So you're given a small data set. On the command line, you give the input directory and the output directory, because of course when you're here and there, you're going to want to give different inputs and outputs. So I think it makes sense to have that there as a parameter. And off we go. So this code, yeah, definitely got to get that hint or that documented somewhere. Okay, so that just read these 4 things, did whatever logic is in the thing, and produced, okay, 1 output file. Because, well, it's pretty small. It's only 250 bytes. So, okay. Yeah, I guess. Like, I don't need a lot of concurrency for 10 rows. I guess I understand that. If I do the exact same thing on the compute cluster, and well, so I'm gonna copy car alarms. Awesome. I'm just gonna copy the code over to the compute cluster. In the other window here where I'm on the compute cluster, I'm gonna run the same basic command. Except the input is in HDFS. It's in this common location. And then, yeah, I can create a directory called output, probably. It takes a little longer. It's going to take a little longer to start up. There's just more mechanics with a yarn cluster. I have to request the thing, and my job has to get started and whatever else. A little network in the way. But that's going to happen. What it's going to do is read those files from the distributed file system that set up something like this, right? So I have in my diagram here replication 3. So one of my workers is maybe on this node. So it's going to read, it's going to read this file locally, and that's great, ideally, read from the local disk. But if it wasn't there, if this node disappears, well, I've still got 2 copies of it somewhere else. And the same for all the other files. So again, I've got 2 things. I can access it as a local disk pretty quickly on a bunch of different places. I can get over the network if not. And then again, if a hard drive fails or whatever, I've got that redundancy. So what I've asked here with my Spark submit command that I ran on the cluster, it's a request to yarn. So there's some config files. Like I have put some, some config files on the cluster that say, hey, Spark, when you're going to submit, don't just run it here, run it out there on the compute cluster. Here's how to get in touch with the compute cluster. Like that's been configured out on there. The default is to run it locally. It's not what I want there. And what I'm doing is like my .py file is really small, right? I'm going to send the py file over to the compute cluster on the gateway. And then from the gateway, I'm going to say, hey, here's my Python program. And whatever work I've got to do, like whatever is going on here, this mod 10 and the group by or whatever, the description of that's really easy to think about. I'm going to send that out to a compute node where it can actually do the work. And that's what happened. And this is why, it takes a few seconds to run something on the compute cluster, because there's just stuff to do. There's accounting and request to yarn. We've got work to do. But while it's working, I can see that. And I don't think, do I have, okay, so what if I do the biggest input set, which is XYZ3? I don't know if I can talk fast enough, but while it's running, I've got this Spark web front end. This one's done. This one. Okay, I want to catch it mid thing. Okay. Okay. I'm not going to reload because probably my job is done as I talk. But what happened there at that moment was I had 4 workers doing work on my behalf. They had taken 4 out of the 10 partitions. No, there's more than 10 partitions there. I can't reload. Oh, maybe I can reload. Anyway, whatever's going on here. 5 out of the 10 things are done, the other 5 are running. And I have this web front end where I can kind of inspect what's going on here. And again, like as soon as the job is over, it this disappears. So this is the only one I can show you without rerunning. But yeah, like I have a little bit of diagnostics here. It was, you know, I'm reading the CSV. That was the start of where things were. So I can see that in the Yarn web front end, and then at HDFS web front end, I can see, I don't know what matters here, but you know, I've got 4 worker nodes, and they're, you know, the disks are this full, and they each have that this much storage, 8 terabytes, give or take. Again, on the Yarn side, I've got the same 4 workers, but now what matters is that they have 15 CPU cores available to Yarn, 16 in total. Yarn has been told it's allowed to use 15 of them. They've got some memory, etc. So again, like I said, it becomes hard to diagnose what's happening because there's just a lot in between you and the actual times of million operation or whatever's going on. But you can kind of get there. And this is one of the tasks for this week, to get to the compute cluster, get your thing running. Okay, I don't think I need that. Let's talk about what's really going on here. Because I've just been kind of like saying the word worker and waving my hands around. My code, like the .py file that I am looking at right here, that's the driver. And this is the code that is running, well, like if I do Spark submit, of course, it's where things start. When I run on the compute cluster, that's what I'm actually seeing run. So I can print, right? I can just do normal Python stuff here. Like I'm not in this code, but I can just like, I don't know. What's happening? Like I can do that, right? No problem. But the actual work that's important, like the actual Spark data frame manipulation, is happening in an executor process or thread, depending on the situation. On the compute cluster, those are on different computers than the one I'm looking at. On my computer, they're still obviously here. Like if I just do on this computer a Spark submit whatever, now I have multiple, I think, threads in this scenario. I'm looking at the driver thread. The worker threads are doing whatever they do. Sorry, the executor threads are doing whatever they do with concurrency. So if I have a lot of threads, you know, that's good. I can get a lot of work done in parallel. On Yarn, I can do the same thing, except on many computers, so I can get even more work done in parallel. Also good. Either way, I'm looking at the driver process. So like when I was on the compute cluster here, like I'm still seeing the output of the driver process. If I run it, again, I can update things. Let's run it on a smaller input set because it's faster. I will still see that print whatever once Spark has started up and is actually running my main function. And it takes some time because now starting my code is a matter of asking Yarn if I can start and where my workers are going to be, where my executor processes are going to be, and if we can do it. But yeah, this still happened. So in fact, most of that time I was sitting looking at this was just the mechanics. My code was working for like a couple seconds at most. But now if my executor processes do something, that's really hard for me to see. They're running on a completely different computer. Like I've said, partitioning now becomes absolutely critical. How my data is partitioned determines the concurrency that I've got. So I could have, if I have unlimited budget and I have a million executor processes on a million CPU cores, and I hand it one partition, well, I've just paid for a lot of CPU cores that I'm not using. Basically, within a partition, it's just a for loop. It's just do all the things, because you got to do the thing somehow, right? And like I said, I've seen people do, in fact, I think the number was 2. They somehow managed to get a data frame with 2 partitions. It was not a student, somebody who should have known better. And we're just wondering, like, well, okay, we didn't have 1,000 CPU cores, but there's how many are there? 60, I guess, right? CPU cores in total? Yeah. Okay, I want to use them, right? If I'm trying to get compute work done, I want to use all my CPU cores. And if my data is partitioned wrong, I'm in trouble. And like I said, it's hard to see, right? I just look at my data, I count the rows, I do whatever. I really don't see the partitioning. My code works either way. I can do, calculate thing mod 10 either way. I can't see that other than my code is now slow. What I need to do is somehow be able to control the number of partitions I've got. And there's no perfect number. It's not like, so certainly what should not be true is you should not come away from this thinking the right number of partitions is equal to the number of CPU cores I have. Because I don't know that every executor is the same, right? There's nothing to say that a CPU core on this computer and a CPU core on that computer are going to run at the same speed. So just not how computers work. Maybe there's somebody else doing something here and these ones are way faster. I don't know. I have no way to know. So the right number of partitions for a data frame is like at least, let's say 10 times the number of CPU cores you have. Okay, so then each executor process is going to be handed, well, on average, 10 things. It's going to be handed 1, and then when it's done that, it's going to be given another one by the driver. Okay, that's fine. 10 is you do 10 tasks. That's reasonable. But again, if some of my executors are slow, okay, they're going to get 8 things done, and some other executors are going to get 12 things done. I'm still using all my CPU cores most of the time. What I don't want is like a million partitions. Then I'm spending all my time just saying, oh, you're done that? Oh, here's another one. You're done? Here's another one. You're done that? Here's another one. So there's definitely a minimum. The absolute minimum is the number of CPU cores I have. I probably want that times 5 or something at the absolute minimum. And then if I have 10,000 partitions, I'm probably suspicious. As I've said many times, and as I genuinely do myself, what I do is I think for a moment, how many CPU cores do I think I have? And I type that number and then I press 0. That's the number of partitions I would prefer to have. It's easy to think about. So, well, let's take a break because it's time to do that. And we'll talk some more about Spark. And as you can tell, it's how it calculates matters because I have big data sets here and I maybe have to think about that. We'll do that more in a bit.